I have f from some domain. Okay, this is abstract definition. I didn't specify what is domain f. It can be whatever crazy thing you want. You can say this is a vector space V, and then what? A norm, with a metric, with an inner product, blah, blah, blah. Okay, but now let's say this thing is an abstract notation. We want this to be a convex set. We don't care what is it. It can be probability measure, it can be number, it can be whatever thing. What is convex set? This. If any S contain 2 points and their line segment is in this set, then it's convex. And we don't care what is this S. So this part is convex. And this is the part that the set is convex. Done. This is why we just have 2 slides. And that's it. But now we talk about this, not the domain, but what is f? You have the following: 1, 2, 3, 4, 5. You can have Yang-Sen's inequality. This, or epigraph of f is a convex set, or first order Taylor series is a global support. This means you need derivative. Or gradient is monotone. This, or if f is twice differentiable, then Hessian is positive semi-definite. Or restriction of f into any subset A is convex. So 1, 2, 3, 4, 5. And here's the important thing. These are all if and only if. That means these are the same definition. This is the most useful one. Then you may wonder why we have so many definitions. Well, it's the same thing as the differentiable. There are 4 derivatives, right? Partial, Garkov, directional, Flechet. Sometimes one of them is useful for some problem. Now the same. We have 5 definitions. Actually, you can keep having the 6, 7, 8, 9, 10. Some of them are useful for some situations. So that's the key point. You need to know which one to use in which situation. And now, these are inequality, right? If I replace this inequality by strict inequality, this is not convex, but strictly convex. That's the idea. So these are equivalent definitions. So let's look at them one by one. Yang-Sen's inequality. What is f? F is from some domain, which is some abstract whatever set, to R is convex if what? Domain is a convex set. 2, for all xy in the domain, this is true. What is this is true? So look at this picture. This is one-dimensional function. That means R1. This is the domain. This is convex set. 1 is true. 2, for any xy in domain, so any xy in this line, okay, that means including this extreme 2 point, okay. We have green below blue. First, this part is red, is this line. This is convex combination of xy, so this actually is xy line segment, okay. Then, this green thing is f, the whole red line. Because of the definition of f, we get this green line. What is this blue thing? We have fx. This is x, then fx is there. Okay, this is y. Okay, then this point go to the y-axis. This is fy. Okay, then what is this? This basically is just linear combination on the y-axis, right? So basically, but if we map it back to this function, we get this funny line. This is saying that if blue is above green, it's convex. This is the definition. Now let me explain. We have 5 definitions. This one have no gradient. And if we do optimization, we need gradient descent, so we need to have some gradient. This one have no gradient. This one have gradient. So that means what? That means this one actually is relatively useless. The advantage of this one is you do not require differentiation. That's true. But for us, when we do gradient descent, we have gradient. Then why not use a better one? So this is the definition. Now we have 2. Epigraph is a convex set. This, a function is convex if the epigraph of f is a convex set. So what is epigraph? So I have a f. Let's say f is just x squared. This is what? This is r to r, or r1 to r. So n is 1, because we can have rn, okay? What is a graph? Graph are all the xy ordered a pair such that y is fx. So that means graph is actually this line, okay? So in this case, this thing is the graph. What is the epi? Epi means above. So epigraph means everything above the graph. So you imagine you have water here. Okay, these are water. You put it here. Then you have water. This thing is a geometric object. This thing is epigraph. So epigraph is also all the xy. But now we don't call it y, we call it alpha or t or h or whatever value we want to talk about. This is not equal, now it's larger than. So for example, my x is 3. Okay, let's say this is 3. My fx will be what? This is my fx, right? This means anything beyond fx. So this is okay, 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 and actually everything on top. So this is epigraph, just a geometric object. This is graph, right? Graph is topologically equivalent to a straight line. So this actually is one-dimensional thing because you can twist it, and then you get this line, okay? So line is a one-dimensional object, even though we are in 2D. But this thing is 2D. So epigraph is 2D. So in other words, what we are doing, if f is Rn to R, this is 1. AP graph is f of what is it? It's something R2. So actually it's 1 plus 1. So suppose if I have Rm, then AP graph will be m plus 1. So actually AP graph is somehow dimension increased by 1. And then we study the convexity here using convex sets. That's the idea. So what's the detail? F is a convex function. That means this is true. Then if and only if this thing is a convex set. Okay, let's look at the proof. The reason why we need to talk about AP graph is because we need to talk about Moore envelope for non-differentiable function, which is detailed later. But now let's talk about AP graph. What is graph? Well, f from x to y. Graph is all the xy such that y is fx. Okay. What's AP graph? AP graph, ignore this for a moment. Ignore this for a moment. Okay. AP graph is all the xy is the same thing. Okay. But then what? Y beyond x. Because we have this means we have an order. So therefore, this y thing will have order. Order means we can compare the size. So we talk about real number. Okay. And this is interesting that we allow positive infinity. And because we allow positive infinity is what is on the top. So we put a bar in R. Let me be very careful. Real analysis does not allow this. We are not doing real analysis. We are doing optimization. We allow this. Okay. So this is called extended real. This is introduced by Terry Rockefeller 50 or 70 years ago. This is very useful. Okay. So we allow infinity. So that means what? That means this R, this thing can go to infinity. But let's ignore it for a moment. And then we also have strict AP graph. What is strict AP graph? It's just AP graph removing the boundary. So that means if I have AP graph like this, strict AP graph means only the red thing, no black thing. Okay. Then what? Here are some details. F can give you infinity, but AP graph do not have infinity. Math reason why this is the case is because this thing is not a vector space. What's a vector space? It's a set with many rules, and one of the rules is you have additive identity. But for infinity, you don't have that. So that's why this thing does not belong to AP graph. And there are extreme cases. What is this? You have a function that is infinity everywhere. Then what? The AP graph is empty set because we don't allow infinity in AP graph. So you have nothing above infinity. So AP graph is empty. That means what? That means AP graph can be empty. And then what is this? This is another funny thing. Every x gives you negative infinity. Then AP graph is the whole space. So imagine I have a function that this black line goes to infinity below, then imagine this red region grow to the full screen. And if this black line go to the top, beyond the screen, then this red region become empty set. That's the idea. These are extreme cases, okay? And of course, we assume this is true. These are by convention. What is the visualization? Well, visualization is just, this, right? And even about the graph f. And now this is funny. This is easy, right? Now let's talk about not so easy thing. My function looks like this. Then my AP graph is, okay, let's say my region is only up to here. Then my AP graph is this. Is this convex set? Not convex set. Therefore, this function is not convex. Why? Youngson's inequality said that any 2 points, the chord need to above the function. Okay, this part is not. So not convex function. Set is not convex set. Function is not convex function. Okay, what about I have a function that looks like this? Okay, then AP graph is this. This is a convex set because first half space, second half space, third half space, last half space. This is the intersection of 4 half space. So this is a convex set. Youngson's inequality. Is this convex set? Yeah. Yeah. So this is convex. These are easy. What about this funny one? I have a function, indicator function on a set C defined as follow. X is 0 if x is in C, x is positive infinity if x is not in C, and now let's say my C is interval 0, 1. Then I have an x line here, this is 0, this is 1. So this function, everything in here will be here. Outside this region, let me assume this is positive infinity, it will be here. Is this convex function? So let me draw like this. So this is filled. This is filled. Okay, this is not filled. So these are empty. Okay, this is not filled. So this is empty. And then let me tell you, AP graph is what? Anything on top of it, right? So anything on top of it is like this, is like this. Okay. But we do not have thing beyond infinity, right? Because AP graph does not allow infinity. So nothing here, nothing here. When we talk about convex set, we talk about the set that is non-empty set. So within this region, it's a convex set. It's like a box. So this function is convex. You may argue, no, this line up to here, this line is not, come on. First of all, this is in infinity. You cannot say I have a line drawing this. This line go to infinity. So this is where Yang-Sen inequality become not so trivial. But using epigraph does not allow R bar, so nothing here. We cannot draw red thing here. So this part is empty set. Empty set, we don't care. So therefore, this function is convex. So indicator function is convex. Then what if this constraint set C is a single point? So what happens if indicator function singleton 0? So this is what? This is like, if x is 0, then it's 0. If x is not 0, positive infinity. Okay? Then we will have what? This thing, imagine these 2 points compress and then become 1 point. So we have, this is the line. And then I have just 1 point here. And then my epigraph will be this. Okay? This is of course convex because it's a line. Right? You say, oh, what about here? No. These are empty set. Empty set, we don't care. That's it. So these are the simple example. Okay? Then, so it's level set. What is this thing? This is epigraph. All the A larger than F. Okay? But now the difference here is this thing, A is given, is fixed, not free. Here, A is free. So for example, this A is 25. Then I'm saying all the Fx below 25. That's called level set. Some people call it sub-level set. It's the same thing. Example, draw a picture. So suppose my function is this, not necessarily convex. This is my f. And let's say this y-axis, this is my a, okay, or alpha. And this is 25. Then level set below 25 is what? All the x such that fx is below 25. That means what? This is the set on x. That means domain of f, okay. All the x, this is true. That means this is the boundary. This part, okay. This part, okay. That means this region is this. So this actually what? This actually is a subset of the domain f, okay. This is on the domain, okay. And here's an important thing. Suppose I have a function that looks like this, okay. And then now this is my alpha, okay. Then I have this. Then what will be the level set? Level set will be this region and this region. So I have two regions. The number of regions actually give you a thing. Remember I said if a set is convex, then it's one connected. Now this is not one connected. You have two regions. This is now using topology argument to talk about the solution set. But these are details. Okay, we don't talk about the detail. We use them. Okay, so this is the idea. Okay, so level set is a subset of domain. So it's subset of Rn. If we talk about Rn, it's not on codomain. We are not talking about R. We are talking about the X. And important one for minimization is this sub-level set because we talk about below the alpha. Then what about the larger than alpha sub-level set, okay, or hypo-level set, okay. If alpha is largest lower bound, then sub-level set is argmin. This is how we define the minimizer of f, okay. And since this is a subset of domain, so this is saying the set of x give me the lowest value, okay. And here's important: this can be empty. So suppose this is this function, no x give you this. This function is fx squared. I'm talking about the alpha here, nothing, empty. So nothing. And then sub-level set can be non-continuous. This is already non-continuous. I have jump. That means something empty, something. It's not convex. This set is not convex because I have two parts. Okay? I told you previously, right? A convex set is homeomorphic to an open ball. This is not homeomorphic to open ball. Okay? So therefore, this is not convex set. Okay? And this is an example. So this comes from the book by Rockefeller and Wetz. So this is a function. This black solid line is graph f. Everything above it is epigraph. Okay? And then this is alpha. This region go to the domain. This part is the sub-level set of f below alpha. This whole black thick line is the domain of f. And this is an abstract function. So this is not one-dimensional case. This is n-dimensional case or even vector space. Or whatever crazy thing you can think of, but we all most likely consider this. So this is also true for what? This is a matrix space, okay, or tensor space, okay. But anyway, so this is a picture. Then why epigraph? Because it's useful. The idea is many property of f has an equivalent form in epigraph, and sometimes it's easier to work with epigraph than f. Like what I said. Why we talk about differentiation with 4 definitions? Because sometimes some definition is easier to do than other. Why we talk about 5 definitions of convex function? Because in some situation, some of them is better than the other. What does better mean? Convenient. Okay. Because there's no true or false here, there's no wrong here because all of them are correct. So therefore, for us it's convenient. So what is this? F is a convex set. So here's the thing. F is a function, domain to real number is a convex function. This is what if and only if F is convex set. So what's the big deal here? The big deal here is this is using language on function, we convert it to language on set. And suppose F set F is closed. Closed means we have solid line. That's the close, right? Then F is convex, F is convex. So this is the idea. And okay, this is what I just said. Any closed convex set can be written as an intersection of half space. So this is the picture. This fake line is graph F. Red thing is F graph. This is a convex geometry. I said any convex body is the intersection of a bunch of convex sets. Therefore, this red thing can be written as a bunch of half space intersect each other. So I have a half space here, and I have a half space here. These two half space give me what? Give me this region. Right? This is not an accurate description of this red object. Doesn't matter. Then I add more. If I add more enough, in the end I get the red shape. Right? This thing can go to infinity. Okay? We didn't say we can go to infinity. This is exactly what I talked about in the slide one. This thing here. Okay? So this is an illustrative example. What is a half space? Half space basically means some inner product larger than some number. Okay, that's right. It's a linear algebra. Okay. So we have the following thing. This is the analysis version of property of F. This is what? This is the geometric version of the property of F. We can call F is proper, F is closed, F is lower semi-continuous, F is convex, and this funny thing we will talk about later. But we can also talk about this. Epigraph is non-empty, epigraph is closed, epigraph is convex. So let's go to the proof. We basically need to prove the double error. What is the double error? F is convex leads to epigraph is convex, and epigraph F is convex go back to F is convex. So this is the two error. Now we prove this F is convex by Youngson's inequality. We have this, right? Any 2 point x1, x2. Remember the red green thing in the picture. This is the red green thing below the blue. So we now have star. Star is F is convex. Second point, because we want this, right? So if x1, y1 in epigraph, that means x1 below y1. This is definition of epigraph, right? Nothing changed. If this is in epigraph, then x2 on F below y2. So this is definition of convexity by Youngson's inequality. This is definition of what? Epigraph. Now, this thing by star is below this thing. Then what? This fx1 is below y1. It's because of 2. So this thing, I replace it by y1. This f2 is smaller than y2. So by 2, I replace it by y2. So now I have this big thing below this thing. What's epigraph? A point, y value. The whole thing is a point, the point. The whole thing is a y value, the y value. This thing is what? Is a Cartesian product. We can split them like this, right? Then we have this. What is this? This is convex combination. And it belongs to epigraph F. So F is convex F. Because T is between 0 and 1. So this proof F is convex implies epigraph F is convex. Now we go to the other way. We assume epigraph F is convex. So by definition, we have this and this. So this is, we consider 2 points. And then what we have? This is convex combination. Convex combination of a point. This is another point. This is what? This is Cartesian product. Cartesian product means you can split, you can put the 1 minus t distribute inside and you can take this. And then you have this. Because they are in epigraph. And epigraph is convex set. So I have this belong to. This belong to is because of the convex set of epigraph. So I have star, star, star. By definition of epigraph, star, star, star is this. Now we have this. What is this? This is actually convex function. So we have this. Convex epigraph gives us convex function. So therefore, what? A function is convex, then epigraph is convex. Now, F is convex. If and only if, that means this is definition. This thing, right? That means the Youngson's inequality, okay? And now we also have epigraph F, which is red region, is convex. I write CVX. We just establish this go to here and this go to here. Now, I'm going to tell you why this is much better.